a video for 5.2, the mean value theorem. And this one picks up with two different corollaries that deal with thinking backwards about functions. And the thinking backwards is basically our integral or antiderivative lesson. So you're going to get kind of a taste of where we're going next based on what these two corollaries state. So first, you have functions with an f prime equal to 0 are constant. So that means if you know that the derivative is 0 of some function, that original function had to be a constant function because the derivative of 0 or a derivative of any number is 0. So again, if f prime of x is equal to 0 at each point of your interval I, then there is a constant c for which f of x is equal to c for all x's in I. So again, if the derivative was 0, then you had a constant function before that. That capital C for constant, we will be using that quite a bit whenever we're talking about working backwards from what that original constant was. And then you have corollary 3. Functions with the same derivative differ by a constant. So if you have that f and g, their derivatives are equal. So if f prime of x and g prime of x are both equal at some point in your interval I, then there is a constant c such that your f of x would be equal to g of x plus c for all the x's in I. So that means even though f prime and g prime are the same, that doesn't mean that f and g were the same, but the most they can be different by was some constant c, because again, if I take the derivative of both sides here, the derivative of c would give me 0, so it would drop out. Many times when you are trying to find what an original function was, you're going to be thinking backwards, but they're also going to give you some point, which we will typically refer to as the initial condition, that will allow you to find out what your c value was. And that's what we have here. It says find the function f of x whose derivative is sine of x and whose graph passes through the point 0, 2. So I know that the derivative of f was sine. So you want to think about, well, what do I take the derivative of to get sine? Well, the derivative of cosine is negative sine, and that's not what I have here. But if I had a negative cosine, its derivative would be sine. However, there could be some possible c for constant that I took the derivative of that dropped out whenever I looked at that derivative problem. And that's where that unknown constant is very important to add to your problem. That's also where we can use this initial condition. Remember, your initial point, that's going to represent an x and a y value. So if we know that it has to pass through the point 0, 2, that means if I plug in 0 for x and 2 for y, I'll be able to solve for my c. So 2 is equal to negative cosine of 0 plus c. Well, the cosine of 0 is equal to 1, and there's a negative in front of that, so that's going to be negative 1. So if 2 is equal to negative 1 plus c, that means 3 has to be my c. We can now replace the letter c with the actual value, and that means the original function f of x is negative cosine of x plus 3. So again, you're thinking about working backwards. By the time we get to chapter 7, we will actually look at formulas for antiderivatives, which is what we're finding here. But for this section, they really just kind of want you to think backwards. So again, antiderivatives, that's what I just talked about. Your function, and usually they'll use a capital F of x to distinguish that you had taken an antiderivative, and I know I didn't do that in the previous question, but I will try to do that from here on out. So f of x is an antiderivative of f of x if your f prime is equal to f of x for all x's in the domain. And then your process to find the antiderivative is called antidifferentiation. By the way, if you type antidifferentiation into a word processing document, it'll probably tell you it's spelled incorrectly, but it is spelled correctly, just as an FYI. And this brings us to example 8. This is going to make use of some of the things that we've already been talking about velocity and position and falling objects. And we have two different sets of conditions here that we're going to go through and find actually the original problem. So we're given acceleration information for both of these. Remember, acceleration is the derivative of velocity, and velocity is the derivative of position. So we need to find both the velocity and position functions, which means that we are going to be going through and doing the entire derivative twice. Can you come back? Sorry, I had somebody at the door there, and doing recording video is not conducive to people dropping into the classroom. So we have our acceleration here is 9.8 meters per second, and the body is falling from rest. So that means that at 0 seconds, the velocity is 0, and that means that if we're starting at 0, our position is going to be 0. So those are going to be our initial things that we're going to be thinking about whenever we go through this. And you can see in part B, it is a little bit different because we do have a different initial velocity. So this one is falling from rest. In part B, it is being propelled at 1 meter per second to begin with. So that's going to change the outcome of our problem a little bit. So we know here that our acceleration is 9.8. So 9.8 meters per second. Thinking about the velocity. Again, velocity, the derivative of velocity is acceleration, so I want to think backwards. I want to think about what I would take the derivative of to get 9.8. Well, the derivative of 9.8t, I'm using t for time because this is all movement type stuff. So typically t is our x variable here. So 9.8t is going to be my equation, but again, there could be some constant c that I might have to deal with in this problem. Now I do know that I have 0, 0 as my original condition. So that means the velocity is 0 at the beginning when time is 0, and that means my constant is 0. So the velocity function is just 9.8t. There is no constant added on there because we are falling from rest, so there's no initial propulsion or anything having to do with that. Now when I find position, I would think, what would I take the derivative of to end up with 9.8t? Well, I do have to go up 1 with my exponent. So that does have to go up to t squared. And remember, if I was taking the derivative of this t squared, I would take the 2 down in front and multiply it by whatever the coefficient of t was to get the 9.8. So if I'm going backwards, I'm actually taking half of the 9.8, which is going to be 4.9. Because 2 times 4.9 gives me the 9.8. And then again, I have some plus c that I need to find because I don't know what my original constant was in this problem. This, I would use the fact that it doesn't say I'm falling from a certain height or I'm starting at a certain height. It doesn't say anything about it. So I know that my position is going to be 0, 0. And you can see when we plug that in, the c for this one is also 0. So my position function is merely 4.9 t squared. Now for part B, it's not going to work out quite that same way because it does tell me I have an initial velocity of 1 meter per second. I am starting with the same acceleration. My velocity is going to start out the same when it's set up, but now I know that for velocity, at 0 time, my velocity is equal to 1. So that's my point for velocity. So 1 is equal to 9.8 times 0, which means my c value here is equal to 1. Because I have a value here now, that's gonna make things different than what they were in part A. So I can't just copy everything that I had in part A because, let's see here, scroll down, give myself a little bit more space. Because if I look at the position, I can reuse the 4.9 t squared. But I also have to think about the 1. We have to think about what we would have taken the derivative of to get a value of 1, and that's t. So 4.9 t squared plus t, and then you still need your c on the end. Now, part B doesn't say that we are falling from any type of position. So for position, I am going to be using the 0.00. Plus equals. And that means that c is also equal to 0 for this position. However, your position function is different than what you had in part A, because it is going to be 4.9 t squared plus t. So you have a few questions like this at the end of your homework assignment for 5.2 that deal with the thinking backwards. Some of them are like the previous example that we had, example 7, I think it was. Some of them are more like this example 8, where you're looking at where they give you an acceleration. By the way, if you are on Earth, your acceleration due to gravity is always going to be 9.8. If you're using meters per second, if it's feet per second, you're going to be looking at, I believe, 64. So just be aware that those are the numbers that you will see over and over again. If you're on other planets, then those values are going to change because their gravity is not the same as ours. So go back through this video. I guess I do have one more slide here. Maybe. Okay. So this is your homework assignment. This is due on Wednesday. It is in Schoology. Go back through the video, read the PDF of the notes. There's a book video you can go through as well. If anything doesn't make sense, please reach out to me because 5.3 is just going to continue building on what we learned about in 5.1 and 5.2. And just like with everything else, please reach out to me if you have any questions.